Hi guys, I wanted to talk to you about solving systems of equations graphically, and I wanted to use Desmos for that. I went to desmos.com and just clicked on the graphing calculator. It's a great one for students. It's free, so they can use it at home without having to have access to a Texas Instruments device. It's also being embedded in a lot of standardized tests, so it's a good one. You can sort of drag it around and zoom in and out, but what I'm going to do is set up I'm going to set up the screen that I want. I'm going to go from -2 to 10, count by 1, and then I'm going to go from -25 to, we'll say 400, 300 maybe, count by 25. Okay, so this is also a lot more intuitive than I think that Texas Instrument calculator, although if anyone wants to know how to use the TI for graphing, please let me know. I could maybe dig one up and do a video on that as well. So that gym membership we were talking about, we had this gym that cost $25 per month. It had a $100 membership fee, right? We can see that here. It starts at $100 for 0 months, goes up $25 per month. We also had that gym membership that cost just $50 a month, not 5. So we have that 50x, but it didn't cost anything to start. So at 0 months, it was free, and then it goes up by 50 each month. You'll see Desmos is really nice because it's color coded. I find that visually graphing systems is difficult for some students because they sort of lose track of which line's which. Colors are great for that. If you notice also the intersection point is really easy to locate and just click on, it gives you the coordinates. This is a nice check for those of you who are sort of practicing those algebraic methods. This is a great way to go back and check your answer other than just plugging it back into the equations. So you'll notice 4 comma 200 is the solution to this system of equations. If it was just purely a math problem, this would be purely the answer we give. What it means, though, is that at 4 months, these two gyms both cost $200. And that's really important to know, but that's not the only thing you can do with systems as far as when you're dealing with real world scenarios. We know if we look at this blue line is lower than the red line, meaning it's less expensive, right? If y is that total cost, then these values are lower on that y-axis. So that blue gym is less expensive at first, right? But then that red gym, it's more expensive because of that membership fee, but by 4 months, you sort of pay that off. And then for after that, it's only costing you $25 a month upkeep. So it's a different answer depending on what question you're asking. Yes, the solution to the system is 4 comma 200, but if I asked a student which gym would you join if you were joining for just a summer, like 2 months, 3 months, they would choose this blue gym. And then you could talk about what if you wanted to join for an entire year, then that red gym would be more affordable. I always have students when I do something like this bring up, well, what about the equipment differences? And that's important to discuss and to acknowledge as well, that not everything is about the math. I did also want to show you another example. So let's say we had another gym that moved into the area. We're going to get rid of this blue gym just because I think it's a little cluttered. We have another gym that moves into the area. It's $25 a month, but it's a $200 membership fee. Not a wise decision from a business model if you're in the same area as this red gym, because what you'll notice is these two lines are parallel. They will never intersect. The reason they will never intersect is because their slopes are the same, but their y-intercepts are different, right? So this guy had a $200 membership fee, but he's going up and over at the same rate as this red guy. Okay, so this is never going to catch up. They are never going to intersect. This is called an inconsistent system. That's not super important. What is important is that you notice that parallel lines will never intersect. Those systems have no solution. Okay, so the answer to this, if you had to solve this, would be there is no solution. They never intersect. You'll note that when you see parallel slopes and different y-intercepts. If two things had the same slope and the same y-intercept, they'd be the same line. And actually, that's sort of a duh situation, 25x plus 100, 25x plus 100. If these are two different gyms, it doesn't matter which one you join mathematically. They're always the same. You will see systems like this come up, but they won't look like this. These are called dependent systems. The red line is underneath this green line. They are always intersecting because they are the same line. this solution would be all real numbers. Okay, all real numbers are solutions to this system, because no matter where you are on the number line, you're intersecting. They don't always look this easy though. Sometimes the format, sorry, excuse all the things happening on my screen. Those are very exciting functions that came up. Sometimes the format will be played with. So negative 25x plus y equals 100 is the same as y equals 25x plus 100. We've just subtracted that 25x from both sides. This is still a same line, all real numbers system, because they are still the same line. You could also see it like this. 50x plus 2y equals 200. What I've done is I've taken that same equation and multiplied everything by 2. Well, we know that if we multiply everything by the same number in an equation, it stays the same. So if I divided everything by 2, I'd be left with that same line. So formatting changes, slight formatting changes, could make it look like these are two very different equations, but when you go to graph them or solve them algebraically, it still could be all real numbers. So those are sort of our three types of systems. Systems intersect at one point. Those are most common. The two special cases is if they never intersect. Those are parallel lines. There is no solution to that. Or if they're always intersecting, meaning they are the same line, that is in all real numbers. It's called a dependent solution, dependent system. The most common that you guys will see is intersecting one time where there is one answer. And I'm going to put 2 more videos up about how to sort of find those solutions algebraically. Because let's say we had something like this guy where it doesn't intersect at a real pretty place, 3.8, 195. There are ways to solve those more accurately.